Start your notes for section 4.2, logarithmic functions. So we'll start with the definition of a logarithm. A logarithm is the inverse of an exponential. So if we have b to the x equals y, so just some base to an exponent equals a number, that can be rearranged into an equivalent statement, log base b of y equals x. So whatever the b, x, and y were in this expression, it would be the same b, x, and y over here. So if we can write like 3 squared equals 9, that's equivalent to saying that the square root of 9 is 3, right? So this is like inverses in action, right? Where it's like two different ways to write the same relationship or the same equation, really. So if we have, let's use different numbers here. 2 cubed equals 8. This can be my b, my x, and my y. Then the equivalent logarithmic statement would be log, so the base of the log here should be the base of the exponent. So this will be log base 2. The number in the logarithm should be what was on the right-hand side. So here is 8. And then it'll be equal to x, which was the exponent. So that would be the 3. So these are two equivalent statements kind of saying the same relationship between the 2, the 3, and the 8. Okay, so we're going to focus computationally for now. So that's what I mean by that is like we're going to be given logarithms to compute. And you can kind of see a few examples below here, right? So compute log base whatever of whatever. So we want to interpret that as the exponent that the base b needs to get to whatever number we're seeing inside the parentheses. So for example, if we're asked to compute log base 2 of 8, we're saying 2 to what power gives me 8? And I'd say, oh, well, there has to be a 3 there because it's 2 cubed that gives me 8. So this logarithm is equal to 3, which we saw in that first example a minute ago. For the next one here, we have log base 2 of 16. So we're saying 2 to what power equals 16? Once the numbers get big like this, it may take a little bit of guessing and checking. I have 2 times 2 times 2 times 2. So this would be 4 times another 4 is 16. So that means 2 to the 4th power is 16. So the exponent 2 needs to get to 16 is 4. For the next one, log base 4 of 16, we're saying what exponent does 4 need to get to 16? That would be 2, because 4 to the 2nd power is 16. Now we get into some more interesting examples with kind of less intuitive outputs. Log base 5 of 1 is saying what power does 5 need to get to 1? And we remember that anything raised to the 0 power is 1. So the exponent we would need here is 0. So this answer is 0. And this would actually be my answer, even if this 5 were a different number. So log base 7 of 1 is 0. Log base 10 of 1 is 0. Anytime you're trying to get to 1 as the output, the exponent you need is 0. All right, this next one is showing us that we can have fractions as the base of a log. The rules for what numbers can be a log base are the same as the rules for what numbers can be our exponential base for a whole function, and that will be any positive number, except for 1. We usually don't see 1. Okay, so here, log base a half of 1/4. We're saying what power does 1/2 need to be 1/4? This squared would be 1/4. So this log is equal to 2. We could also do log base 9 of 3. we're saying what exponent does 9 need to get to 3? And this one's really unusual because the square root of 9 is 3, right? This is like trying to get smaller. So because the square root of 9 is 3, that would be the 1/2 exponent. So this output right here is 1/2. I'm going to include one more example here before I talk about those special bases down below. Why don't we do log base 3 1/9, just so that we can see another example of a strange output here. So this one is saying, what power does 3 need to be 1/9? And again, it's like the last one where how to get from here to here with an exponent is not quite as intuitive as some of these earlier ones. So I know to get a 9 from a 3, I would need to square it. And then to get it as a denominator, I would need it to be a negative number. So what I actually need in that spot is -2, because 3 to the -2 power would be 1/3 squared. So this logarithm is equal to -2. So what we're starting to observe here is that the outputs of a logarithm can actually be anything, right? We've got positive big numbers, we got 0, we got fractions, negatives. You can actually have any number be the output of a logarithm. All right, let's talk about a few special bases. So there are 2 bases for logarithms that get used more than the rest of them. And so they get special notation just because they're really common. So this first one, if you see a logarithm that just doesn't have a little number on it, the little number is implied to be base 10. So this is the same as log base 10 of x. And we use it a lot just because our number system is base 10. So powers of 10 come up a lot. This next one is ln of x. The ln stands for natural log, I think in French, which is why it's in the opposite order. But we would say this either ln of x or the natural log of x. And this represents a log with base e of x. All right, so let's practice a few of these down below. The first one is log of 100. All right, so without a number written here, we're going to assume that the base of this logarithm is 10. So really we're looking at log base 10 of 100. So we're saying, okay, 10 to what power gives me 100? 10 squared gives me 100, so this will be 2. Natural log values are tougher to compute without a calculator. There's only a handful that we can really do anything with. This is some of them. So ln of e, this is the same as log base e of e. So we're saying e to what power gives itself? Well, that would just be 1. The next one, ln of 1, we're saying e to what power gives me 1. And just like above here, we said log base anything of 1 is 0. Same thing here. We know e to the 0 would be 1. So we still have a 0 output here. All right, we'll go to the next page. There's a little bit more to talk about before we're done. So there are some really fun properties of logarithms that we're going to talk about together. And I've highlighted just the 2 inverse properties in this video, and this is where we'll end. So y equals b to the x and y equals log base b of x are inverses of each other. All right, so before I even talk about this right here, come back to our scratch paper. So for example, the function y equals 2 to the x, its inverse is y equals log base 2 of x. These 2 are inverse functions of each other. Or if you have y equals 5 to the x, its inverse is y equals log base 5 of x. I'll do one more. Y equals e to the x. Its inverse function is y equals log base e, which is the natural log of x. Okay, so one important thing we learned about inverses a while ago was that if you compose them, right? So if f and g are inverses of each other, then f of g of x gives x, and g of f of x equals x, right? Because an inverse is supposed to like undo what the original function did. So if you do g of x to something and then apply its inverse, you should just end up where you started. And so that's where we get the two properties that we see here. So if the b, the base of the logarithm and the exponential are the same, then log of exponential cancels out, or exponential of log cancels out. All right, so let's see these in action in a few examples. Here we have log base 2 of 2 to the 7. So essentially this is saying, what exponent does 2 need to be 2 to the 7? Well, that's just 7, right? So it's sort of like log base 2 and 2 canceling, and just the 7 comes out. So this is showing what this first property was trying to say. So log base 2 of 2 to the 7 just spits out the 7. Same thing here. The log base 3 of 3 to the something is just going to spit out the something. Or you could think about it with the extra step and say, okay, what exponent does 3 need to be 3 to the negative 2? Well, that should be just negative 2. ln of e to the 9 looks a little different, but because ln is log base e, this is kind of similar to the last few, right? So log base e of e to the 9, the ln and the e to the cancel, and just that exponent comes out. So this cancels to 9. Similarly with the last one, this is the common log, so it doesn't have a base stated. We're going to assume that the base is 10. So log base 10 of 10 to the minus 6 cancels to minus 6. All right, and then these last few examples have the second inverse rule. So the second inverse rule said b to the log base b of x just cancels out to be whatever was in the log. So here, if we have 3 to the log base 3 of 7, it'll cancel to just the 7. So we could think of this as using that inverse rule, or you could kind of think with an extra step about what it's asking us to do, right? So log base 3 of 7 is whatever exponent 3 needs to output 7. We're saying, okay, whatever that exponent is, 3 of that. So whatever it was should output 7, right? All right, in the next one, we have 5 to the log base 5 of 9. 5 and log base 5 will cancel, and I get 9. E to the ln of 2. Again, it looks a little different, but it's still in the same theme. It's e to the log base e of 2. So it's just 2. And then finally, with the implied base 10 here, 10 log base 10 cancels, and this would be just 3.